1. Hi. Today we're going to have a look at X-ray diffraction and how Bragg used X-ray diffraction to find out the structure of a crystal. The basic principle behind X-ray diffraction is this. If I take X-ray and I shine it at a substance, at a sample, it can either be transmitted, in which case it will continue along the original direction, or it will actually be scattered by the electrons in the atoms of the material. Now, all the atoms in the path of the X-ray will actually scatter the X-rays. And what I can do is, once these X-rays get scattered by the atoms, I can have a look at the constructive interference that's made and then make a deduction based on that. Now, so here's the example, right? Let's just say here's a structure, it's a crystal. I take some X-rays and I hit it. And that should be drawn as a wave as well. Now, what has happened is we can see that the second X-ray has actually traveled a greater distance than the first X-ray. We can simplify this diagram like this. There's no reason to draw it like that, and we can just simplify the diagram to be like this. Now, as I said, this X-ray has actually traveled a longer distance than this guy. If we take these two waves back and we put them together, so let's say that's the first wave, and because the second wave has traveled a greater distance, it's going to get there a little bit later. So it's going to look like this. So we can actually see that we're not going to get constructive interference because the peak does not align with the peak. The only time I will actually get constructive interference is if the extra distance it travels is equal to the wavelength. So for example, it has to be late by one entire wavelength, or two entire wavelengths, or three or four. And in that case, what will happen is it won't make a difference. This guy is late by one entire wavelength. And we can see that now it actually aligns exactly. It could also be late by two entire wavelengths, 1, 2, and then it gets there, and then this peak will still align with this peak. My diagram is a little bit inaccurate, but you get the point. So, constructive interference will only happen if the extra distances traveled is an integer multiple of the wavelength. This, in fact, gives us Bragg's law. And Bragg's law, said simply, is just this. N lambda equals 2d sine theta, where n is just a number, 1, 2, 3, 4, 5, 6. Lambda is obviously the wavelength. So wavelength. D is the distance. This distance is d. Distance. And theta is actually the angle. We can actually prove Bragg's law just by some simple trigonometry. So let's try to have a look at maybe a simplified diagram of this, and I'll just label everything. This angle is theta, and I said this, in fact, is d. We'll draw a line perpendicular from there, and we'll call this A, B, C. Up until this point over here, these two waves have exactly the same distance. And these two waves have exactly the same distance as well. The extra distance that the second ray travels is in fact AB plus BC. And what we can actually do is, if we just use some simple trick, and I'm just going to take that diagram and I'm going to draw it separately. So we're going to get maybe a diagram that looks like this. A, B, let's call this point X over here. X, we have the 90 degrees in theta. And if you look at this, we get XB, which is the distance. We get AB equals D sine theta. So this distance turns out to be D sine theta, and this distance turns out to be D sine theta. So the total distance that they actually travel is 2D sine theta. And that, in fact, gives us Bragg's law. Now, as I said, the constructive interference will only happen if the extra distance is traveled is an integer multiple of the wavelength of the ray of light. Now, what can you do with this? What you could actually do is, you could use this to find the internal structure of a crystal, because you can use this to find D. You know the wavelength, you know n, and you know the angle at which you're propagating it, so you can actually find the distance D. In fact, Bragg had already used this to find the internal structures of quite a few crystals, and he used this to also find the structure of a diamond. This actually also led to X-ray crystallography, which is, again, used quite a bit even now, and it's used quite extensively.